I would like to introduce our first presenter for the Enhanced Train Control and Operations technical section, Dr. Luc Faucher. Dr. Faucher is the director of CEFRAIL, a rail expertise center with a mission to consolidate research, technical assistance, and training activities related to railways at Cégep de Sept-Îles. Dr. Faucher holds a doctorate in materials and metallurgy engineering. He is the chairholder of NSERC Industrial Research Chair for colleges in railway operation and maintenance since its launch in 2013. The chair's industrial partners are ArcelorMittal, I should know how to say that since I buy their stock, Rio Tinto, IOC, Tshiuetin Rail Transportation. So welcome, Luc.
Well, thank you, Kevin, for the introduction. And I would also like to thank the organizing committee for this conference and letting me present today's research. Today's subject is the assessment of the aerial system to detect and analyze the condition of angle bars on the 260-mile railroad. And as Kevin just mentioned, it has been done at our research center here in Sept-Îles with the collaboration of ArcelorMittal. So, first, what is the aerial technology? Well, it's a technology that has been developed by a company named RailMetrics in Quebec City, and it was initially designed to inspect road and landing strips. They have sold this system in over 40 countries, so the big question was, can we also inspect the track with that system? So this is the system that we do own here at the college. It's mounted on a highway pickup truck, but the system can also be on a car. And it is mounted here at the back with these sensors that are there that will do 3D mapping of the track that is under it. So some technical feature of the system, you can see here some the laser lines that are sent on the ground. And you will collect this laser line with a special resolution of 1 millimeter and a depth resolution of 0.1 millimeter. The acquisition width is quite wide since the cameras are high. It's 3.6 meter wide, and you can do your survey during day or night. And in the end, you will get these 3D images that are here. But where we mostly work with these top images in 2D, which can be represented in two different modes, which is the intensity mode and the range mode. So here the intensity mode, well, it means that of the 100% of light that was emitted on the ground, what is the percentage that comes back to the cameras? So when you have a smooth reflective surface like the top of the rail, you will have a high intensity. And when you take a look at the ties or the ballast, well, there will be some absorption and deflection. So this part of the images will be darker. And you can also take a look at the picture by range, which means that when the components is closer to the cameras, they will turn to be bright white, like the top of the rail. And as you go deeper to the surface, this is darker. And after that, the system uses machine vision with AI algorithm to detect the components and their condition. And you can see here that the ties has been highlighted in green. You can see the spike. You can see here the joints with the angle bars. You can also take a look at the plates, the rail anchors. So you can almost see anything that you can see from the top of the track. And many studies were run with this system to confirm that it works on really short tracks and at the loop at the TTCI. But what will happen if we go on a longer railroad? And this is why the partnership with ArcelorMittal, this is where it begins. So this is the track that is in the northeastern part of Quebec. As you can see on the picture here, it's a quite remote railroad. Only accessible by the road on very few places at the south and at the north. And if we take a look at this track here, well, it is a link between the mines at the top from Fermont to Port-Cartier. It is a class 3 railroad with continuously welded rail, and it is a 136-pound grade of rail. So as I mentioned, it's mainly used to carry the iron ore from the mine at the north to the south. Every year, it's about 26 million tons of iron ore that are carried on this railroad. And the north part here, because there are two mines, has a higher density of traffic because there is a 16 million ton of run-of-mine ore that is carried at the north. So the north section is quite used during the year. It's 80 MGT per year. So the study that we ran with the system was to assess the angle bars. So the company used standard angle bars of 36-inch long, but well, they will be fixed with 6 bolts if the joints are permanent, or only with 4 bolts if they want to weld it before winter. So, well, we did our survey to this study during the month of July, where both types are present. And we did the inspection at expansion speed, so which is 25 miles per hour. And we took a survey of all the 260 miles, which in the end gonna give us images like these. These images, we have 412,000 images because, well, each section represents 1 meter. So when you go on a 260 mile long railroad, you kind of have 412,000 images in the end. And as you can see here, well, we can really see the angle bars and also the nuts with the bolts that are there. So for an angle bar that has 6 bolts, you can count them here. So 1, 2, 3, 4, 5, and 6. And if there are only 4 bolts, it's the same. It's quite easy to take a look at it. So, well, the 2 main questions during the study was, is the system capable to detect all angle bars? And also, was the system capable to count the right number of bolts that there are at these angle bar? So to do that, we made our own software to extract and visualize the data. And let me tell you that, well, because of the high definition, it's kind of 2.5 terabytes of data that we do have to process at the end of the survey. So, of course, we need some help, which is with AI in this case, with the deep convolutional neural network that is used. And, well, it's quite important to assess the angle bars, since sometimes some nuts can break. So as you can see here, of the 6 bolts that there were before, there's one that is missing right here. And, well, you can see that this bolt is just next to the angle bar there. So if we have a system that is able to detect the angle bars, to count the number of bolts, and also at some point the opening of the gap here, it would be great. So, well, to be sure that the system was capable of assessing the angle bars, we took a look at 4 different key performance indicators. The first one is precision. Well, precision is of all dimensions positive by the DCNN, which percentage is truly positive. So it means that when you get an image and it says that, okay, there's an angle bar there, sometimes it will really have an angle bar, which is a true positive, but sometimes there won't be any angle bar, so that will be a false positive. So of all dimensions positive, what is the percentage that is truly positive? We also took a look at the sensitivity or recall, which is the capability of the DCNN to find all positive in the database. And to do that, of course, you have the true positive, which are the real positive, and also false negative, which should have been positive. So what is the proportion of true positive that we do have regarding all these positive in the sample? So the third parameter here is the specificity. So regarding specificity is to know if, well, the system of all that should be true negative, which percentage was mentioned negative by the DCNN. So it's the same as we just seen before, but this time for the negative. So at the same time, of all the negative in the sample, what is the proportion that are true negatives? And the fourth key parameter here is the accuracy. So of the ratio of correctly labeled subject to the whole pole of subject. So of all that says that were positive or negative and that in fact were true, what is the proportion over the whole pole of subject? So the first thing we took a look at was to know if the area system was able to detect all the angle bars. So what you can see here in the green circles are all the angle bars that we found on the track with the system. And to restrain, I would say, our research, we randomly selected a 3.5 kilometer of track, which turns to be a sample of 3,500 images. So if I zoom in, this is the section that was assessed. And it turned out that in that section, there were 30 angle bars that were present. So in the end, what we expect from the system is to have 33 positive images and 3,470 true negatives. So here's confusion matrix that we did after the study. So what you have here are the predicted value by the DCNN, and here are the real values. So what you can see here, for example, you have 29 positive values that were predicted by the system that are in fact positive, but there's one that was negative, but was mentioned as positive by the system. And when you take a look here, you will see what the system says are negative. So there is one that was in fact positive, but the 3,469 others were really negative. So this is how now we can calculate the 4 parameters. So the precision here, as I said, is of all the one that are mentioned positive, which what is the percentage that is really a positive one? So that will be 29/30. So the precision here is of 96.7%. When you take a look at the sensitivity, so of all that are really positive, what is the number that we know that the system says that are really positive? So that would be 29/30. So the same percentage here for the sensitivity. And after that, well, we took a look at the specificity. So this is the same, but for the negative. So as you have 3,469 that are real over 3,470, when you round up, you have a 100% result. And for the accuracy, which is the number that are really are well defined by the system, which is almost all of the data here, you have an accuracy of 99.9%. So what we can see is that, yes, the system has the capability to detect angle bars. So now, does the system is able to count the right number of bolts? So what we did at this time is that we randomly selected 30% of all the angle bars. So on the track, there were 2,220 angle bars. So 30% of that main sample of close to 700 images. So this time, the confusion matrix is for multi-class classification. I won't go into deep as the previous part, but what is important to see here is that what you have in green are the number of balls that were right. So there were a few of them that were wrong, but in the end, the system has good performance indicator. The precision is quite high, over 97% as a sensitivity. And the specificity is close to 92% and the accuracy to 98%. So what makes the specificity a little bit lower is that, in fact, there were some angle bars that were identified that were real angle bars, but they were not on the main line. They were on the in the siding, but in the switch. So the system wasn't able to recognize that these angle bars were in the siding and not in the main line. So, well, we need to better define which angle bars are in the siding, and this number will, of course, increase. So in the end, the conclusion is that the system has the capability to count the number of bolts. So what is to take a look at in the future? So you can see also two other parameters that are really important at angle bars, which is the joint gap here, and also if the angle bar is broken. So when we take a look at this angle bar with the system, before it was highlighted in yellow, you can see here that on the cameras, we can see that these angle bars are broken. And also we can see here the joint gap. So the system already gives information about the joint gap, but we need to confirm that this information is right in the end. So as a conclusion, what I can say here is that the performance of the DCNN developed with the area system to identify angle bars and count the number of bolts meet expectations. Also, the precision, the sensitivity, specificity, and accuracy to detect the angle bars were all over 96.7%. And many false positives came from real angle bars, but were detected on the wrong path in switches. So a better recognition would be better for the next step to go on. So I would like to acknowledge the people at ArcelorMittal, at Real Matrix, and also the research staff here at the Cégep de Sept-Îles for this study, and also all the funding organism that we can see here on the slide. So thank you very much, and if we have time, I'll be more than pleased to answer questions.
Perfect. Thank you so much, Luc. There does seem to be a question from Marina Zhang. How fast and easy is it to deploy the method to the entire scanned region?
Well, it's quite easy. You only come there with the high rail truck, install it, and you don't need to configure it. You don't need to set to calibrate the system. It's already calibrated because all the compensation is already in the cameras, and we always have good and well-defined images without needing to do calibration more than once a year. So, well, you just go there with the high rate, you start the system, and in less than 2 minutes, you're ready to take the data.
Interesting. And I'm just going to ask a question myself here. Where do you see this system being utilized further along rail lines instead of just angle bars? Because it seems to be quite accurate at that. So what's the future considerations for this technology?
Yeah, the technology, what is interesting is really the fact that you see everything. You see the ballast and you are able to see if it's aggregated, if you have too much ballast or if you have a lack of ballast. You can see also the quality of the ties because you have a definition of the cracks. You can see also if the tie plates are sunken or not. You can see also the height of the spike. So if in a curve, for example, the spike are starting to lift up, you will be able to see that. So, well, we're working a lot. I didn't show necessarily the results today, but to take all this data and make it talk by section or by different spot on the track and give results about this and help the maintenance of way to plan what is next to change. And even we want to go with change detection. So to see if in a curve, for example, the wear is increasing through time, because we also see the wear and the defects on the surface of the rail. So the system is really promising, but what we need to do is to be able to get the result fast, since we have big data, and to give the result as fast as possible. To get all these results today, it takes 3 days of post-processing, but we want to shorten this time and be able to give results as fast as possible.
Perfect. Thank you very much. There is one more question, but we're out of time. We're going to move to the next presentation. You could take the time to just type out an answer if you want in the Q&A box.
All right, my pleasure. Thank you.
Merci beaucoup, Luc.